Hi, and welcome back to the new robotics workshop. In this lesson, we're going to learn how to use sensors that share a large amount of complex information using communication protocols. First, we're going to learn what a communication protocol is, then how to use a few of the most common protocols with Arduino. Finally, we'll use a communication protocol to add an inertial measurement unit to our rover and build a new finite state machine to navigate around an obstacle. Up to now, we've primarily looked at robots with one onboard computer, in this case our Arduino, acting as the robot's brain, managing a lot of other simpler components. Sometimes though, this isn't really an accurate model of how robots work. Most complicated robots are networks of different processors, each managing their own complicated task, from motion planning, driving, sensing, or controlling actuators. In this case, each of these processors need ways of sharing information so they can all work together in harmony. The techniques used to share information between processors are called communication protocols. Fundamentally, digital communication between processors is all about taking the output of one processor, connecting it to the input of another processor, and agreeing on the meanings of different logic levels and timings. Digital data is represented with a base 2 number system, where each digit or bit can have a value of either 0 or 1. It's easy enough to assign a value of 0 to a low pin voltage, or 0 volts, and a value of 1 to a high pin voltage, or 5 volts in the case of the Arduino. By setting our pin voltage low, we can send a 0, and by setting it high, we can send a 1. The thing is that integers other than 0 and 1, floating point numbers, and alphanumeric characters are all represented with groups of bits, so we need to send more than one bit in a message. If we can agree on a timing convention to communicate when one bit ends and when another begins, though, we can send one bit after another in a process called serial communication. Using serial communication, we're able to send the groups of bits necessary to form larger messages. One method of coordinating the timing involved in serial communication is called synchronous serial communication. In this method of serial communication, the two processors are connected by a common ground, like always, a data wire for serial data, and a clock wire that the sender uses to indicate when a bit of data on the line is valid. Assuming our clock is rising edge active, indicated by this arrow on the rising edge of the waveform, each time we raise the logic level on our clock to high, the receiver knows to read a bit of data from the line. So in this case, the first time we raise that clock line to high, the data value is 5 volts, or a high logic level, so we read that as a 1. Next time we raise the clock line to high, it's at 0 volts, or low, so we read that as a 0, and so on and so forth. Another method of coordinating serial communication timing is called asynchronous serial communication. Asynchronous serial does away with the clock wire in favor of stricter structuring of each message, and each processor carefully maintaining its own internal clock to determine when the data is valid. This determination of validity is based on the concept of bit time, which is the duration of time that a single bit of data is present on that data line. The communication processors must agree on the bit time to send and receive a clear message. For asynchronous serial communication, the data line is set to high in its idle state, which we also refer to as its marking state. The beginning of a message is indicated when the data line drops from that high marking state to the spacing state at a low logic level. This marks the beginning of the start bit. The start bit lasts 1 bit time after which the sender transmits all the bits of the message, each lasting 1 bit time. Typically, these messages will be 8 bits long, although 7 is also relatively common. The first bit transferred is called the least significant bit, or LSB for short, while the final bit is the most significant bit, or MSB. After the MSB, the stop bit is sent to signal the end of the message. After the stop bit has been sent, the data line is again free to send another message. These are simply the fundamentals of how serial communication protocols work. The communication protocols we'll discuss in the remainder of this lesson build on these foundations to make data transfer fast, efficient, reliable, and suit the needs of different users. We'll discuss these differences and learn the basic tools to use each of these protocols in an Arduino-based project. The inter-integrated circuit bus, also called I2C or I2C for short, is a synchronous serial communication protocol that has become popular because it's fast, can link more devices than asynchronous protocols, and requires fewer wires than other synchronous protocols. To connect devices over I2C, the SDA pin on each device must be connected to an SDA bus, shown here in red. The SCL pins on each device must likewise be connected to an SCL bus, shown here in green. It's important to remember all these devices need to be connected to a common ground, but we're going to omit that from our diagram for simplicity. Any I2C message is broken up into frames. The first is a 7-bit address frame, which the controller uses to name the peripheral device it intends to communicate with. After the address frame comes 1 or more 8-bit data frames, depending on the message length. The controller may send these data frames to a peripheral or request them from a peripheral. The controller, though, decides when communication happens and what device it communicates with. Arduino microcontrollers offer some convenient tools for working with I2C communication. For one thing, our diagram isn't quite an accurate representation of an I2C bus. The SDA and SCL buses each idle at high logic levels. This is accomplished using pull-up resistors, which are sometimes included in diagrams of an I2C network, but Arduino devices have built-in pull-up resistors, and so we don't have to think about them too much when assembling our I2C circuit. Another really great tool that Arduino offers for I2C communication is the wire library. The wire library provides a variety of different functions to make communication between devices over I2C simple for Arduino projects. Later in this lesson, though, we'll use a sensor with its own custom I2C library. Custom libraries are common for different breakout sensors that are largely designed for hobby use. These custom libraries, though, are generally built on top of the wire library and add just a few functions to make interfacing with the sensor easier. We'll explore this more after we discuss 2 other serial communication protocols. Another great tool that Arduino offers for I2C communication is the wire library. The wire library provides a variety of different functions to make communication between devices using I2C simple for Arduino projects. Later in this lesson, we'll use a sensor with its own custom I2C library. Custom libraries are pretty common for these breakout sensors that are largely designed for hobby use. These custom libraries are generally built on top of that wire library, though, and add just a few functions to make interfacing with the sensor easier. We'll explore this more after we discuss 2 other serial communication protocols. An SPI circuit is a bit more complicated than an I2C circuit. Just like I2C or any synchronous serial protocol, there's a clock line, in this case called SCK. Unlike I2C though, communication from the peripheral to the controller, or CIPO, is performed on a different bus than controller to peripheral, or COPI. Finally, the chip select, or CS, pins are used to identify which peripheral the controller wants to talk to in a multi-peripheral system. An SPI peripheral knows to communicate when its CS pin is pulled low. When its CS pin is high, it ignores the controller. This makes addressing peripherals simple, but it means the controller must have as many CS pins as peripherals it communicates with. The actual message that SPI sends can be a lot simpler than I2C, but that's because the hardware required to send that message is more complex to make up that functionality. Just like with I2C, it's possible to create your own serial communication program, but Arduino provides the SPI library for SPI communication. This library includes functions to make SPI communication simple for the Arduino programmer. Finally, we get to a serial protocol that's a bit different than anything else we've discussed. The Universal Asynchronous Receiver Transmitter, or UART protocol, is an asynchronous serial protocol versus the previous two synchronous protocols we've discussed. Remember, that means that UART forgoes a shared clock wire to keep the devices in sync with each other. It instead relies on strict standardization and timing of messages. This makes UART communication slower than the previous two communication protocols we've looked at, but it does simplify communication from a hardware perspective. This is all the wiring that UART communication requires. Just two wires, and a common ground as always. Unfortunately, UART is best for connecting only two devices, so this protocol isn't great for building the larger networks of devices we can put together with I2C or SPI. It's still a useful protocol, and when we're using the serial class, you may recognize some of the commands as the same commands we use to interact with the Arduino serial monitor. This is because the Arduino IDE uses UART to upload compiled code to an Arduino device and receive data from the device to print to the serial monitor. As you may have already figured out, the serial class provides built-in UART functionality for Arduino projects. Because it's a class, we use it a little bit differently than the functions provided by the previous libraries we've discussed in this lesson. The serial class comes from a pre-installed Arduino library called hardware serial, which automatically creates the objects serial and serial1 from the serial class. You can use the serial object to talk to UART devices over the USB port, and you can use the serial1 object to talk to another UART device you've plugged into the TX and RX pins on the Arduino. Because timing is so critical in asynchronous communication, every time we use UART communication, we need to tell the device how fast communication will occur. The speed of UART communication is described by a baud rate, which we can specify in the setup function with the command serial.begin. Remember, serial refers to the object that communicates over the USB port. If you want to talk to another device over the TX-RX pins, you'll need to call the begin method for the serial1 object instead. The argument to the begin method is going to be the baud rate. 9600 and 115,200 are common baud rates for communication with the Arduino IDE. As long as we get that set up properly, we're free to use other methods provided by the serial class, such as read, write, and print line, to communicate with other devices over UART. Communication protocols give us the ability to network processors, which results in robots that run fast and are easy to modify and repair. We'll practice using a communication protocol, in this case I2C, by connecting an inertial measurement unit to our robot and using it to navigate around an obstacle. An IMU is a device that detects orientation and movement using a suite of accelerometers, gyroscopes, and sometimes other sensors such as magnetometers. Each of these sensors have different strengths and weaknesses, but by using sensor fusion techniques to combine data from each sensor, it's possible to track the IMU's motion with more accuracy and precision than you could with any individual sensor. That's beyond the scope of this workshop though, and for today we're going to use individual sensors on the IMU to try and give our rover the abilities of a compass and a level. Before installing our IMU, we need to solder on some header pins so we can press it into the breadboard. That process should be familiar by now, but we're going to walk through it one more time. So in this case, we don't need or want to attach all of these header pins. Our IMU comes with the option to use a few different communication protocols to talk to it, but we plan to use I2C, so we only need to feed it 5-volt power and connect the SCL and SDA pins. What we're going to do, we're going to snap off 6 header pins. Come down here, make sure I grab 6. 1, 2, 3, 1, 2, 3. There we go. That should be 6. So let's test it. Lovely. That fits. All right, so I'm gonna take my header pins, I'm gonna press them into a breadboard like we did before. I'm gonna make sure I get the side with V in, ground, SCL, and SDA, right? Because SCL and SDA are the pins we want to connect for that I2C protocol. Just like we've done before, I'm gonna solder one pin and then reheat it to make sure I get the angle I want. Great. All right, so we've got a bit of that droop, but that's no problem. We learned how to deal with that already. Perfect. Now my sensor isn't drooping, so I'm gonna go through and solder the remainder of these pins. All right, let's give that a moment to cool. Take it out and inspect my joints. I got a little more solder than I wanted to on a few of them, but generally I think they look good. I'm gonna set my soldering tools to the side for now, turn off my iron and let that cool down. All right, now I'm gonna grab my rover. I'm gonna take my IMU, and we're gonna look at the mini breadboard, make sure we get things plugged in where they're supposed to be. So what we want is these pins we just soldered, the side with the SCL and SDA pins. We're gonna make sure that they are on this side of this big old gap in the mini breadboard. So you see where my pins are, gonna press them right in between these wires, and there we go. We want to make sure that there's enough space to insert jumper wires behind it. So to connect the IMU, we need 4 jumper wires. So I'm gonna come over and grab a few. I'm gonna grab a black, a red, and then I'm gonna grab a green and blue. I'm gonna separate my green and blue, and now we are going to twist these guys together. Cool. So to hook up our sensor, let's first focus on the sensor side of things. So thing number 1 is we have a V in and ground pin. I'm gonna connect my red wire to that V in pin. I'm gonna plug my black wire into the ground pin. Then I'm gonna do green into SCL and blue into SDA. All right, so you can see the order goes red, black, green, blue, at least if you're using the same colors and doing the same thing I did. All right, so with red and black, it's simple. We wanna take our our wires to the 5-volt bus, just like we so frequently do. Plug them right in. Make sure the red wire goes to the hot side of the bus and the black wire to the cold side. There we go. So next I need to plug in my SDA and SCL wires. So what we're going to do is we're going to plug the SCL pin, which if you remember is the green wire, into I22. I imagine it is a nightmare for you all to see, but behind these red and blacks here, I got that green wire into I22. Next, we're going to take our blue wire, which is connected to the SDA pin, and we're going to plug it into I23. So again, a little bit of a nightmare, but such is often the way of things with wiring. Perfect. Just be careful that you don't mess up any of the other rat's nest going on in here. It looks like I got that down in there. So you can see these green and blue wires are now going down to I22 and I23. So by connecting the SDA and SCL wires in that fashion, we've just created that wire diagram that we showed for the I2C portion of this lesson. All right, now we have the IMU installed and we need to write some code to talk to it. The first step in this process is to get all the libraries that we need to work with this IMU. This IMU is called the ICM20948, and Adafruit produces some libraries specifically for that sensor, which make it easy to use. So the first thing we're going to do is go open the Lesson 5 Advanced Sensing.eno code. Alright, so first thing I'm going to do, we're going to go open up the library manager, and we are going to look for Adafruit ICM20X library, and we're going to install that. So you see here it says that it's got some dependencies, the Adafruit Bus.io library and the Adafruit Unified Sensor library. I'm going to hit install all so that it also installs those dependencies. If for some reason yours doesn't install those dependency libraries, then go ahead and look them up and install them separately. Alright, so we're going to go under line 15, include communications libraries. We're going to start including all these different libraries. So that's going to be hashtag include Adafruit ICM20X.h. Alright, we're going to go include Adafruit ICM20948.h. We go include Adafruit sensor.h, and we are going to include wire.h. So this is also a good place to create the sensor object, which provides us with the methods we need to interact with that sensor. So I'm going to go ahead and do that as well. Right here under what is for me line 21, create the ICM object. So the way we do that is we go Adafruit ICM20948 ICM semicolon. So that should go ahead and make me an object called ICM. So now we're going to go on to that setup function. We're going to give ourselves some troubleshooting tools in this code with some print statements so we can keep track of the startup process of our IMU in the serial monitor. We need to begin UART serial communication with our Arduino to allow this, and that means, as we discussed before, setting a baud rate. So let's go down to set up ICM 20948, line 87 for me. Serial.begin 115200. And we'll add a little setup handling. While serial object does not exist, delay 10 milliseconds. So that little setup error or setup delay handling, that's not necessary, but it gives the serial bus some time to start up before we do anything else. So we also set that serial baud rate to 115,200. When we open the serial monitor to view data, we need to specify the baud rate in a little drop-down menu on the right side of the monitor. Otherwise, everything we see will be gibberish. Next, we're going to try to start I2C communication with our IMU chip. So all we need to do that is call ICM.begin I2C to attempt to initialize our device. It isn't strictly necessary, but we're also going to add some simple error handling logic that lets us know if initialization is unsuccessful and enters an infinite loop so the program doesn't go on any further. So here under our little while delay statement, we are going to add serial.getLine Adafruit 20948 test. Smiley face for good vibes. We are going to try to initialize the sensor with if begin I2C. We go serial.println failed to find IMU sensor. And then we will say enter the infinite loop while delay some arbitrary value. Cool. And if that doesn't happen, if we do find the IMU and don't enter that infinite loop, then we want to go serial line, let's go ICM 20948 found. Smiley face again. Because if that happens, I'm happy. So after creating the necessary additions to that setup function for our IMU, we want to create a new function that gets the magnetometer data from the sensor and converts that data into orientation in degrees. We're going to call this function getAngleMag, and it'll return the orientation as a float data type. The first step is to call the method that gets us new data from the IMU. So we're going to go down to our getAngleMag. As we said, we are going to call those methods that get us new data from the IMU. So sensors event t Excel, then we go sensors event t gyro, sensors event t mag, sensors event t, and the line we're going to use to get that data is ICM.getEvent, and we're going to get that data gyro mag temp. Alright. Now that we have this data, we need to figure out a math equation we can plug our magnetometer data into, which will spit out our robot's angle. To do this, we need to consider what our magnetometer data means. So figure 13 in the ICM 20948 datasheet shows us the axes of the magnetometer compared to the housing of the chip. When looking from above, such that the dot on the ICM 20948 chip is in the top left corner, The x-axis points to the right, the y-axis points down, and the z-axis points away from you, into the page, following the right-hand rule. What the magnetic field sensor does is measure the magnetic field strength in microteslas along the x, y, and z axes of the magnetometer. This gives you the vector components of the local magnetic field. So, in other words, our IMU with this axis orientation in this 5 microtorr magnetic field going that direction, that would return these values. For mag.magnetic.x, we read 3 microtorrs. For mag.magnetic.y, we read 4 microtorrs. Simple enough. The vector components of the magnetic field are useful to us because we can use the trig function arctan to find the angle of the magnetic field vector. If we can determine the direction of the magnetic field of the Earth relative to our robot, we can compare the orientation of our robot to something that doesn't move. So let's plug -4 and -3 into arctan. When we do so, we find we get 53 degrees. Sounds normal enough, but remember the orientation of our x and y axes. When we plot that 53-degree vector relative to our chip, we realize it's directly opposite the magnetic field that we were measuring. So what gives? Well, for one thing, we have 2 negative vector components, and negatives cancel. It appears to the arctan function then that it's just the same as having 2 positive vector components. A similar thing happens when you have only 1 negative vector component. In that case, either vector component could be negative, but arctan won't discriminate between the different possibilities. Essentially, arctan can't tell the difference between graph quadrants 1 and 4 and 2 and 3, the diagonally opposite graph quadrants, and so it will always assume that your vector is in quadrants 1 and 4. What we need is a version of arctan that can discriminate between these various cases. Luckily, Arduino provides the atan2 function for this exact situation. This function calculates the output of arctan and then considers the signs of the vector components to determine which quadrant the vector is actually in. We'll use atan2 for a get angle function. A few final details are atan2 outputs an angle in radians, so we'll use a conversion factor that Arduino provides called rad2 degrees to get angle in degrees. We'll also input the negative of the y component to atan2, which essentially just rotates the axes of our magnetometer so the y-axis points towards the front of the rover. Alright, so we are going to go back to the code with our getAngleMag function. Under what is line 170 for need, determine angular position, we are going to plug in our function. So we're going to do float angle equals atan2 times rad2 degree negative mag.magnetic.y over mag.magnetic.x. Alright, just do that. No slash for division, it does that on its own. Alright, following that, we are going to simply ask our function to return angle. Alright, I'm going to grab my robot, make sure it's up on a stand. The last code we ran on it drove the motors, although they're not driving right now. Oh, fully qualified port name. USB serial port. Go nano. We're going to try now. And we're getting errors. Magnetic. So it goes. upload that sketch. Okay, to actually see it, we need to uncomment a few lines. So now let's upload that. Then let's go to our serial monitor, plug in, oh yeah, you see we get gibberish in the serial monitor. So let's set our baud rate. It's not returning anything. I wonder why that is. Let's go print mag magnetic y. Let's just see what happens when we do this. Yeah, it kind of looks like it's just getting zeros. So our chip is on, it's got power. Who is on the SDA? Finding the sensor. I would sure be curious if there were something wrong with mine in particular. Try swapping some pins just for fun. That was not the case. It was connecting before, now it's not. So we had the configuration of it. Worth a shot. You know what might be happening? I think we may have forgotten to include some code. That's okay. So up here in setup ICM 20948 IMU, this whole section in the setup function, we're going to paste this big code block. We're going to see what happens. Nothing. Okay, so that code block was to set the magnetometer's, essentially to set its data rate, which is an important parameter in determining the data we receive from the IMU. The thing is that the magnetometer data rate is by default 100 hertz, which is what we're going to set it to, which is why we didn't include that line of code previously. Oh, yeah, maybe I just swapped some line of code. Okay, there we go. Now we're getting some data. Look at that, way better than it was before. So sometimes the solution to coding is, don't mix some things up when you're reading and writing a whole bunch of lines of code. So to recap that, what the problem was is this line down here, 170 ICM.get event, I swapped this and mag and temp lines in the code. So if for some reason you find yourself getting nothing but zeros from the IMU, then that would be something to check. So now that we're successfully getting values from the IMU, I want you to take a moment, look at the values you're getting. How accurate do you think they are? What might cause the behavior that we're observing from these values, and are there any ways that we might be able to improve the performance of this sensor? Now that you've had the chance to go through this process with the magnetometer sensor, I would like you to try to do it with the accelerometer to interpret the direction of the gravity vector. So give it a shot yourself by filling in the get pitch function, and here's a little hint. Accel.acceleration.x will return the acceleration measured by the accelerometer in its x-axis. Before we wrap up, let's use our new and improved sensing capability to create a rover which can navigate around obstacles and keep moving in a set direction. A simple way to do this is to have our rover, when it gets close to an obstacle, turn right, drive a certain distance, then turn back to its original direction to see if the obstacle is still there. If it is, the rover will turn back right again and drive. If not, the rover will continue forward on its original path until it sees another obstacle. We can use a finite state machine to solve this problem just like in the last lesson. This state transition diagram shows a finite state machine structure which can perform this task. Imagine it's a little hard to read in the video. I recommend going to the write-ups or the Jupyter notebooks in order to get a better look at this diagram. This time, it's up to you to program the event checkers and actions that will drive this finite state machine. Reference the diagram and the finite state machine that we built in the previous lesson for help. We need the switch case structure, which is already in the main loop. So we go down to the main loop. I'm gonna re-comment my test lines that I was using before. And there's, for me right now, it's line 130. Put your FSM in here. I'm gonna remove this block comment. And that opens up the switch case structure that will be essential for building this new finite state machine. Use this switch case structure and fill in the event checkers and the actions with your own code. Depending on your comfort level with the programming we've done so far, this could be a pretty challenging task. If you feel stuck, I recommend you work and collaborate with your team members or other people you may be doing this project alongside of. You can also go back, revisit the state transition diagram and code we used in the last lesson. To make this task a bit more approachable, the code already includes a function called getAngleOdom. GetAngleOdom is almost identical to the getOdom function we wrote in previous lessons, but it uses forward kinematics to find the angular position of a robot rather than the linear position. It's easier to use this function rather than the getAngleMag because the unreliability of the magnetometer you probably observed earlier. Once you've gotten your rover to navigate around an obstacle, make sure to commit your changes to your repository and push those changes to GitHub. This has been a tough challenge, and good work for sticking with it. This wraps up the hands-on portion of the workshop. The final lesson will be an overview of more advanced robotic topics. You can explore these if you feel you're ready to tackle some harder problems.